Okay, we are going to talk about electronegativity, okay? And this is defined as the ability of an atom to attract electrons towards itself in a covalent bond. Now, some atoms are better at doing that than others, okay? So we have a little think about, let's think about the top row of the periodic table. We've got carbon, nitrogen, oxygen, fluorine, and then we've got neon. Right, I'm going to forget about neon because look, it says in a covalent bond. Neon doesn't form a covalent bond, any covalent bonds, so we can forget about that. So which element do you think would be the most electronegative out of carbon and out of fluorine? Well, you've got to attract electrons towards yourself, so which one has got the most protons in the nucleus? Okay, well, carbon's got 6 and fluorine has got 9, so I think fluorine is going to be the best at doing that. It's going to be the most electronegative, but we've also got to think not only number of protons, but we've also got to think about the distance of the bonding electrons to the nucleus. Now, for carbon and fluorine, it's going to be about the same because the electrons involved in bonding, I'm going to go just using, I'm not going to use sp notation, right? Carbon is 2,4, so the electrons are in the second shell, and fluorine is 2,7, so the bonding electrons there are involved in the second shell as well. Fluorine's going to be a little bit, it's going to be about the same size, but fluorine's going to be smaller if anything. Remember, the electrons get pulled in closer as the positive nucleus increases, so fluorine would definitely be the most electronegative there. Okay, let's have a think about chlorine and bromine here. Now, which would be the most electronegative? So that's it. This is group 7 of the periodic table, isn't it? Okay, which one would be the most electronegative out of chlorine and bromine? Well, we've got to think about the number of protons. Bromine's got more protons, but chlorine, the electrons, the bonding electrons are in shell 3. Whereas in bromine, they're in shell 4. So they're closer to the nucleus in chlorine. So chlorine is actually the most electronegative. So I always think it's quite a useful little thing. If you ever want to measure it, if you ever want to think about the trends in the periodic table with trends in electronegativity, in the periodic table, if you think like that, okay, increasing. So the further up you are, the higher electronegativity because you're closer to the nucleus. That's this arrow here. And the further to the right you are, the more electronegative you're going to be because you are because you've got more protons in the nucleus. Okay, so shall I fill in the rest of that bit of a periodic table there? So we've got, just try and tidy this up a bit. So we've got fluorine, let's move chlorine, bromine, then I've got iodine, I've got sulfur and phosphorus there, and I've got silicon here, I've got boron here, and don't forget our little zigzag line, which is showing metals from non-metals, is going to be like that, isn't it? Yeah. Okay, so really these are the elements we're most interested in. We're not really that interested in boron, are we? But if we look at the top row, well, we've got our carbon, nitrogen, oxygen, and fluorine, and we're interested in the halogens, and phosphorus and sulfur, fairly important. Okay, so we can see there that probably fluorine is definitely the most electronegative element, and we'll talk about the positions of the other ones in a bit. But let's just see what it means. What effect does it have? And it has quite a big effect. Let's think about hydrogen and hydrogen chloride. Okay, so HCl, hydrogen chloride, gaseous HCl, covalent bond there. You've got a pair of electrons in that bond. And remember, we're talking about molecular orbitals. So we'd say, right, really, what's that going to look like is you're going to have you're going to have the electrons in there. But chlorine is more electronegative, so it's better at attracting those electrons towards itself. So rather than it being that shape, sort of exaggerated, the electron density might look something like, so I'll rub that out, the electron density might look something like this. Okay, so chlorine is getting more than its fair share of the electrons. And that would mean chlorine has it's slightly, this end of the molecule, this end here, is slightly negative. You've got more negative charge at this end compared to the amount of positive charge than you have at this. So this end would be slightly positive. And the way we show that normally is if you draw, so you wouldn't try and draw the electron density, but you put a little delta sign, delta minus and delta plus. That means delta means it's a little bit of an electron. If it was just minus, it mean the chlorine has got a whole electron more than it should have. It hasn't got that much. It's just got a bit more than it should have. And the hydrogen is not H plus, but it hasn't got quite as much of that electron as it should do. And we can say that this molecule has got a dipole. Okay. We call this a dipole when you've got this uneven sharing of electrons. We'll talk about that a bit later. But what effect does that have? Well, it means if you had liquid hydrogen chloride, I just making some HCl molecules, and this is liquid hydrogen chloride. Well, this one would be a little bit negative at this end, wouldn't it? That'd be a little bit positive. Sorry, I've drawn positives there when I said negative. A bit negative there. So that means it would be attracted to a neighboring HCl molecule. I'm going to draw there, H there, and Cl, because this end is a little bit positive, this end is a little bit negative, and there'll be an attraction there. Okay, and that's called well, that's a type of intermolecular force, which we'll talk about later, but it holds them together. And so at GCSE, you talked about intermolecular forces, but you never said what they actually are. And hopefully now you should have some appreciation of what the nature of intermolecular force is. So that was our introduction to electronegativity, and we'll talk about that more in the next video.